When people interact with a language model, they see an autoregressive text generator, a system taking a prompt and churning out words one by one. But in production environments, these models do something entirely different. They operate as execution engines, triggering APIs, running code, and manipulating databases with rigid precision. The frontier of artificial intelligence research has moved past generating fluent conversational responses. The engineering objective is now autonomous procedural task execution. To understand how a system built to predict text can operate autonomously, we have to strip the system down to its mathematical bedrock and trace the engineering stack all the way up to the software loop. That means tracking the data through the underlying probability vectors, into the sequence processing algorithms like transformers and state space models, and finally into the agentic frameworks that grant the model autonomy. A model that only predicts conversation is a chatbot. A model that predicts the exact syntax needed to execute external tools becomes a functional application. Human text is broken down into discrete tokens and mapped to precise numerical IDs. Those IDs are then linked to a token embedding matrix. Every token is assigned a static array of floating point numbers, locking it into a specific mathematical position. The language model takes those static, independent vectors and processes them together. It incorporates the surrounding tokens to output contextual embeddings, vectors whose numerical values shift based on their position in the sequence. This creates a distributed representation of language. Semantic meaning is defined entirely by spatial geometry. Words with similar meanings cluster together in this high-dimensional latent space. To organize this geometry, models are trained using an objective called cross-entropy. By minimizing cross-entropy, the model iteratively adjusts its weights to reduce the divergence between its own probability distribution and the actual distribution of the training data. The system does not comprehend language. It optimizes geometric proximity to minimize statistical prediction errors across billions of data points. Transformers process this data using self-attention, comparing every token in a sequence to every other token simultaneously. But this creates a bottleneck. As sequence length grows, compute power scales quadratically. Double the sequence length, and you quadruple the processing cost. For autonomous agents performing complex multi-step tasks, holding hundreds of thousands of tokens in memory is a hard requirement. The quadratic scaling of pure transformers exhausts GPU hardware before those massive context windows can be reached. This hardware limit is driving the adoption of state space models, or SSMs. Architectures like Mamba and Jamba maintain the context capabilities of transformers, but change the underlying math to process sequences much more efficiently. Here, we can see the difference. While the transformers' compute demands explode, the Mamba architecture achieves linear time sequence modeling. The compute requirement scales proportionally to the sequence length, dramatically lowering the memory footprint. Bypassing that quadratic bottleneck is exactly what enables modern models to hold millions of tokens in active memory without crashing the hardware. Even with massive memory, a model is trapped within its own parameters. Its weights are mathematically frozen at the end of training, isolating it from any new information. This pipeline shows one method for breaking that isolation: retrieval augmented generation, or RAG. The system connects to a document retriever, pulls external data, and feeds it directly into the context window to construct an informed answer. But fetching text only solves half the problem. Trying to train a language model to perform rigid mathematical logic using only statistical approximations requires massive amounts of compute and still yields inaccurate results. This image highlights the engineering alternative: tool use. The model evaluates the prompt and uses cross-entropy optimization to output strict, bracketed API calls. It predicts the exact character strings, like 400 divided by 1400, needed to trigger external calculators and search engines. By predicting the syntax that commands external software, the system completely bypasses the limitations of its own frozen latent space. In computer science, an artificial intelligence agent is classically defined by three components: sensors to perceive an environment, a planner to make decisions, and actuators to alter that environment. In a modern AI architecture, the user prompt acts as the sensor. The external APIs act as the actuators. And the language model itself serves as the central planner. This node diagram illustrates how that planner evaluates its options. The model generates probabilities for different actions, routing the system down specific execution paths based on statistical likelihoods. To chain those decisions together, engineers wrap the model in a procedural software framework called REACT, standing for Reasoning and Acting. The REACT loop forces the model to articulate a thought, execute an action, and process the resulting observation. If the task is incomplete, the loop feeds the observation back into the model to trigger the next cycle. Wrapped in this framework, the language model is no longer a passive text generator answering a single prompt. It operates as the central processing unit of a continuous, autonomous software cycle. The REACT loop gives the system autonomy. That loop is powered by predicted API tool syntax. That syntax is generated by efficient sequence architectures like state-space models, and those models are driven by the raw geometry of cross-entropy optimization. Artificial agency is not a simulation of human intent. It is highly optimized probabilistic token generation, routed through a procedural execution loop. The underlying mathematical principles of language modeling have not changed. What has changed is the target output, from generating conversational text to generating precise operational parameters. As foundational algorithms shift from modeling language to modeling executable actions, software engineering transitions from writing deterministic code to orchestrating complex probabilistic systems.